same phase space factor, which is a blocking factor. You cannot scatter into occupied states. And since this depends on temperature, you can actually have a temperature where the eigenvalue of this equation is slightly smaller, or in the limit equal to 2 times the chemical potential, which is the upper limit of your MEC. If this happens, the system wants to go into a paired state. All the particles want into this correlated. We don't have a Slater determinant anymore, which is a particle wave function. Let us go from the other side. Let us suppose that the interaction is so strong that we have a bound state, like in the deuteron, which was also discussed in the last lecture. So, and if the deuterons are far apart, you can forget the Pauli principle. And we have, if one can forget about the Pauli principle, the deuterons can be considered as bosons. And we have seen yesterday that if you have bosons, you can put all the bosons in the same state. So a natural ansatz for the wave function here from R1 to Rn is just the product state of the same wave function n half times, because you have this is a condensate wave function which all the bosons in it. So then squeeze this and in such a case your critical temperature is just here for the deuteron at minus the binding energy per particle, which is 1.1 MeV. Now if you squeeze it, you start to feel the Pauli principle, and you have to put an antisymmetrizer. So it gets a very complicated wave function actually. And in the case of pairs, this technical procedure to calculate everything with this wave function, which has been invented by Bardeen, Cooper, and Schrieffer. So I will not explain to you how to handle this wave function, but I have told you that you can, for example, calculate as a function of chemical potential the occupation numbers. And the occupation numbers, we remember, these are the occupancies pair in the infinite system, pair momentum state, and pair spin state. So if the deuterons are very far apart as a function of, let's say, epsilon p, the wave functions are occupy very little of the phase space, but it happens some moment where the phase space gets more and more occupied, and you cannot pass beyond 1 in the for Fermi systems. Okay, you know that the Pauli principle prevents you to occupy more than one state, one particle per state. So it saturates here, and it goes eventually in this kind of shape. And this you can do with antisymmetrized wave functions. I will not explain you this whole theory of Bardeen, Cooper, and Schrieffer. It's generally abbreviated by BCS theory. And I gave you a homework to do to see that the 2-particle level density which enters into the solution of this equation has a finite value at the Fermi energy or at the chemical potential. And this is where, here's the chemical potential essentially. This is where the correlation shows up with respect to a pure step function which you have in the non-paired case. This is the non-paired case. And I told you that it's seen also here on the view graph that in the four-particle case there's a strong difference with respect to the two-particle case, namely that the critical temperature in the alpha particle case, it starts also out here at 0 temperature at -7 MeV, then goes sharply up, but it breaks down at a value of mu which is close to 0, and this happens because the four-particle level densities for quartets at rest go to 0 at 4 times mu, which is 4 times the chemical potential. And I don't know whether Angela Bonacorso gave you the homework to do to show yourself why this level density goes to 0 in the four-particle case and not in the two-particle case. So there's a strong difference in the physics in the alpha particle condensation case. We can only go up to here, and I also showed you a Vru graph somewhere. I think should have it somewhere again. Here you see here are the occupation numbers in the case of the quartet and the deuteron. It goes up here to very small values for negative mu's and goes up a little bit, but it stops at mu values slightly positive, and you cannot go beyond. The equation has the four-body equation has no solution anymore. So that's a strong difference, and I told you that in this case the two-particle problem is a very particular case in the many-body physics. All clusters beyond 2 cannot go in this intermingled phase of the deuterons or 2 electrons, and in the four-body case we have no such dense alpha particle system. It only has the Bose-Einstein condensation phase. Okay, this was essentially what we discussed yesterday. We then came to the finite system, finite nuclei, and I told you about the Hoyle state, which is in carbon-12 a very important, one of the most important states in nuclear physics. This was the state at 7.65 0 plus state, and the second 0 plus state at 7.65 MeV. And I told you that this state is the entrance state for the triple alpha reaction, that because of beryllium-8 is unstable, and this state enhances very much the triple alpha reaction. Triple alpha, alpha plus alpha goes over first to beryllium-8 plus alpha, and then finally it goes into this excited state at 7.65 MeV. And I told you that astrophysicist Hoyle was somebody who predicted the states on more or less entropic grounds, which means he said, I'm full of carbon-12, and so there is so much carbon-12 in the universe that there must be an acceleration mechanism where this reaction goes into carbon-12, and he predicted this state a couple of years before the state was discovered. So then we went on saying that this state remained mysterious for a long time. In the 60s, 70s, and in early 70s was Horiuchi, who was the first with a phenomenological theory who explained this state. And it was not a chain state like was it predicted by Morinaga, and it was a state in his theory where the alpha particles in S state, which means homogeneous spherical distributions, the alphas turn around in relative S states, and so later then in the mid 70s, again two Japanese, Kamimura and Uegaki, with a 12 nucleon wave function, achieved to calculate this state very accurately, and I will try to explain to you how they managed to calculate and what their theory is. So Kamimura made the following ansatz. Kamimura et al. At around 1975, they made the ansatz for the 3 alpha wave function, which was proportional to center of mass part with Jacobi coordinates, psi1 and psi2, and 3 times the intrinsic alpha wave function, which you remember was also its relative coordinates with a small b parameter, so it was e to the minus r1 minus r2 squared and so on over a small b parameter, which is the extension of the alpha particle in free space, which is a radius of about 1.4 Fermi. So these so-called Jacobi coordinates, where the 3 alphas have this psi1 and this is psi2, which are the only coordinates which remain if you subtract this total center of mass motion of the wave function. So this is a 12 nucleon wave function, and the only open wave function was this center of mass wave function. So they calculated the expectation value of a Hamiltonian for the energy was equal to 3 alpha h 3 alpha over the norm 3 alpha psi 3 alpha. So they calculated with a given Hamiltonian with a two-body force, which has been adjusted prior from alpha-alpha scattering and so forth. This is so-called Volcker Force. I don't want to go into the details here, but they minimized this expectation value with respect to the unknown function chi. So all these are given functions, so they could integrate and made the expectation values with respect to all these relative distances, and at the end they remained only with a Hamiltonian. Let's call it psi1, psi2, psi1 prime, psi2 prime, chi of psi1 prime, psi2 prime is equal to the eigenvalue, and there is another difficulty from this ansatz, because these wave functions are not orthonormal, so there is on the right hand side exists also what one calls a norm kernel, psi1 prime, psi 2 prime, chi of psi 1 prime, psi 2 prime. And this norm kernel, for example, has the following shape. Is relatively complicated expressions. Norm kernel is psi 1, psi 2, psi 1 prime, psi 2 prime is of course the one function of psi 1, psi 2, but then you have to integrate over all these squares of the intrinsic alpha wave function. I don't write this out. This is integral, multiple integral over all these coordinates from R1 up to R4, R5 up to R8, and so on, of this phi alpha wave function, phi alpha, and so forth. And you have here again and all this has to be antisymmetrized. You can imagine that this is, and if you end up with such an effective equation for this unknown function, this is not a real Schrödinger equation, because you have a kernel also on the right hand side. So this is the sign that this wave function psi of chi of psi 1 and psi 2 are not orthonormal. So before you start the calculation, you have to calculate, diagonalize this norm matrix and see whether the some eigenvalues are 0 or not 0. And actually it happens that this norm matrix has 0 eigenvalues, and this space of 0 eigenvalues has to be eliminated. You cannot calculate this Schrödinger equation where the norm matrix has 0 eigenvalues. So you can only diagonalize in the space which has, where the norm matrix has finite eigenvalues. I don't can go into details. You can imagine that is a, in principle here, a three-body wave function. Any three-body problem, if you reduce it to the Jacobi coordinate, depends on these two Jacobi coordinates, and already in free space the three-body problem is a difficult problem, and here you can imagine that it is. So at that time in 1900 in 1975, it was really an extreme exploit from these people, Kamimura-san, and with a slightly different technique, which I will explain you later. Also Uegaki, practically at the same time, solved with a microscopic 12 nucleon wave function this difficult problem, and explained the Hoyle state at the right energy. So if they diagonalize this Hamiltonian, they don't only get the one state, they get several states. And for example, one of the states they predicted was a 2+ state. The second 2+ state, the one has also here first 2+ state, which is a pure shell model state. They predicted it at about 9.9 MeV. And this state has only very recently been discovered or found experimentally unambiguously by Martin Freer and Moshe Guy, which had very sophisticated experimental techniques to find this state. The difficulty was that there is a third 0+ state close by, which has a large width, which covers this second 2+ state, and so experimentally it was very difficult to disentangle. But in 1975 they predicted this state, and it only very recently was found. So you may argue that this function here somehow is preconceived for the 3 alpha particles. And it's true, they, in some sense, they inserted the physical idea that the Hoyle state is a loosely bound ensemble of 3 alpha particles, and they said, well, the 3 alpha particles I don't touch, I give a intrinsic wave function here and only calculate the center of mass part of the wave function. So in 2005, the other people came with other theories and wanted to explain the Hoyle state, and these are what one calls anti-symmetrized molecular dynamics approach, which I also want to shortly just sketch for you. I mean, these are complicated many-body calculation. I cannot go into all the details here. In what one calls anti-symmetrized molecular dynamics, also Horiuchi was one of the inventors of this theory, and the wave function has the following form: psi anti-symmetrized molecular dynamics is equal to a norm, an anti-symmetrizer, and just a repetition of the same wave function, phi 1, 2, phi 1, R1, phi 2, R2, and so forth up to phi n, Rn, and the whole thing anti-symmetrized. And the trick here is that the phi i's of Ri are just Gaussian wave functions. Gaussian wave functions of the following form, not normalized, are e to the minus Ri minus Zi, also vector, over 2 times width. So these Zi's are actually complex functions. Zi's are Ai's plus Ib, complex numbers, and if the betas are real, this is called AMD. If the betas, the widths, are also complex, this is called Thermionic molecular dynamics. So AMD, essentially invented also by Horiuchi. FMD, people from Germany in Darmstadt, Feldmayer and Neff invented this. Feldmayer and Neff. So why can you can ask the question, why can one use here an anti-symmetrized wave function of simple functions? Well, the point is, and this I give you as homework also, that if you put this, the center of all the Gaussians to the origin, the anti-symmetrizer makes out of this product of Gaussians theta determinant of harmonic oscillator wave functions. So this anti-symmetrization of the Gaussian makes S wave, P wave, D wave, and you get for the z coordinates going to 0 complete Slater determinant of harmonic oscillator wave functions. And in the homework which I give you, I ask you to show the following, that for a two-particle system, namely for psi of x1 in a one-dimensional case, psi from x1, x2, a norm, and you have Gaussian displaced e to the minus x1 minus s squared over b squared times e to the minus x2 plus s squared over b squared, and you antisymmetrize this and take the limit as the s or the z factor here goes to 0, limit s goes to 0. So these two Gaussians are displaced left and right from the origin by s. So you have a wave function where you have one Gaussian concentrated at x1 is minus in s, and another Gaussian which is at x2 centered as at plus s, right? You antisymmetrize, you take the limit as s goes to 0. You should find an Slater determinant of the first state, the first harmonic oscillator, which an even state in 3 dimension is an S state, and this is a P state, is L equals 1. So it's an odd wave function, and you should find that you have at the end as a solution, I give you the solution, that is indeed a Slater determinant, that psi of x1, x2 is equal to x1 phi of x1 is the Gaussian, x1 times phi of x2 minus phi of x1 times x1 x times x2 x2. So up to a norm. This is just an antisymmetrized Slater determinant of the lowest two states. So this is an odd function. This is the Gaussian. This is the Gaussian of the lowest state times phi x2 minus the Gaussian at x1 times the odd wave function. This is a Hermite polynomial in one dimension. So this is a nice exercise to see that such an antisymmetrized product of Gaussians can actually have many configurations possible depending on the position of the Gaussians and the width of the Gaussians. Actually, when this is imaginary, a complex number, this simulates some velocity. So if you take this as z real plus I some momentum, so this should be squared, you get here a factor e to the minus r squared or I squared minus IP r product plus a term which is pi squared, p squared over 2 beta I squared. And you see that this simulates a moving wave packet. So you have in the choice of this parameter can either be if the to the origin, or the wave packets can move around in space and form, for example, an alpha particle if 4 two neutrons and two protons come here on the same space, you can form an alpha particle. And so depending on the choice of these many parameters here, I are the number I are as many parameters as there are nucleons, or even more if you're in 3 dimensions. And also the width, either it is real, then it's AMD, antisymmetrized molecular dynamics, or it's also complex, which is more difficult, of course, because you have more parameters, but eventually also more powerful. Then it's called the Thermionic molecular dynamics. And you calculate the expectation value of the Hamiltonian with these wave functions, and you minimize the energy with parameters. Calculations. There is no a priori indication of any alpha particle there. There's no, all depends what the minimization of the energy gives you for the parameters. So if you do that, it was found by also again a Japanese lady, Enyo, Canada Enyo actually is a double name. Who found for the whole state the following configuration. Such alpha particle configurations came out for the Hoyle states. For example, for the Hoyle state, one of the configurations was this one. I told you that there's also a third 0 plus state at around 10 MeV, where this is similar, a little bit similar to the linear chain state. It's not exactly elongated, but more similar to the chain state postulated by Morinaga, whereas the Hoyle state has such a beryllium 8 configuration, a little bit farther away, the third alpha particle, and you have to imagine that this should all be averaged over space in a relative S wave. So it's not, there are other calculations, yes, unfortunately it's upside down, but you have here another calculation with FMD, and you see actually the Hoyle state has several different configurations for 3 alpha particles, and so it's not a unique ensemble of 3 alphas, indicating that you have actually a superposition in as a relative S wave of this Hoyle state. So these are calculations with no a priori indications that the Hoyle state is an agglomerate of 3 alpha particles. So this was a confirmation of the ansatz of Kamimura and Uegaki, which I will tell you a little bit later, that indeed the Hoyle state is built out of 3 alpha particles, and that the ansatz of Kamimura was justified. Okay, well, this showed that actually, I mean, they also found and they confirmed the first calculation, more phenomenologic, of Horiuchi, that the Hoyle state is built out of 3 alphas in relative S waves, but at that time nobody talked about the condensation phenomenon. What about the condensation phenomenon? And I mean, these calculations were so complicated and so successful in 1975 that afterwards nobody did any calculations anymore about the Hoyle state. It stayed sort of dormant for about a quarter century, 25 years or something like that. In 2001, I proposed with my colleagues Japanese colleagues and one colleague in Germany, condensate wave function for the whole state, which has the following structure. So the authors were Tosaki, Horiuchi again, myself, Schuck, and Röpke from Germany, from Rostock, for University of Rostock, Röpke. In 2001, we proposed the following. We said, this wave function in the meantime became known as the so-called THSR wave function, according to the initials of the four authors, as proportional again to an antisymmetrizer, and we have written this wave function already several times. And now 3 alpha particles, like for the deuteron, 3 alpha particles, alpha R1 up to R4. Again, the same wave function, R5 up to R8. And the third alpha particle wave function, R9 up to R12. So it's also a 12 nucleon wave function. I don't write up the spin and isospin indices here. Alpha spin wave function S total spin equal to 0, and also isospin wave function, total isospin wave function to 0. So I don't write it out because it's a trivial part of the wave function. The most interesting is the coordinate part of the wave function. So we wrote such a antisymmetrized 3 alpha particle wave function, and you remember that this, of course, since it's 3 times the same wave function, it sort of indicates condensation. It's some preconceived condensation ansatz, and we thought, let us try to calculate this. Of course, this is an extremely complicated 12 nucleon ansatz, and it's, for instance, complicated because of the antisymmetrizer. If you have to antisymmetrize explicitly these 12 coordinates, it's very complicated. So you can only solve this with an ansatz. So we took the following ansatz for this alpha particle wave function, and we will see in how much it is motivated. So we took for 1 alpha particle, let's say from R1 up to R4. It's proportional to an exponential of the center of mass. This is minus 2 R1 minus xg squared over some Witz parameter squared times this usual intrinsic alpha particle wave function, which depends only on the relative coordinates R1 minus R2 absolute, R1 minus R3 absolute, and so forth, which you have seen already several times now. So this is a intrinsic Gaussian ansatz for the wave function with a small b parameter. Another b parameter, I should nevertheless write it out, for R2 squared and so forth over another width parameter. So actually, and this is the center of mass of 1 alpha, the first alpha particle, so it's R1 is 1/4 over R1 plus up to R4. And the xg, this is actually center mass of coordinate of all the so it's xg. xg is actually 1/3 of R1 plus R2 plus R3. So in this way, also the center of mass part of the wave function, of the total wave function, depends only on the relative coordinates of the center of mass coordinates. So it's capital R1 minus capital R2, and so forth. It generates again these Jacobi coordinates. So this is a ansatz which depends only on two parameters, namely the width parameter of the center of mass part and the width parameter of the individual alpha particles, small b. And we will see that small b, if we take it also as a variational parameter, it will stay more or less at the free space value, as the capital b parameter can cover the total volume. Actually, this ansatz with these two Gaussians, if the capital B parameter is equal to the small b parameter, it is just a Slater determinant. You can see that in the following way. If you have two Gaussians, R1 squared over B squared times e to the minus R2 squared over B squared, and if you introduce now center of mass coordinates, R1 is 1/2 R1 plus R2, and let's say small r is R1 minus R2. And if you express R1 and R2 by the center of mass and relative coordinates, you have R1 is capital R1 minus R relative half, and R2 is R1 again. This is plus, and let's call this minus R half. So if you insert this here into this expression, you get here e to the minus 2 R1 squared, or let's call it simply R squared over B squared e to the minus R squared over B squared. So you see, in a harmonic oscillator wave function, you can very easily separate the center of mass motion wave function, but the center of mass wave function has also the small width, which of course, if you want to have an alpha particle condensate and such configurations where the alpha particle move around in the whole volume of the carbon-12, you should not have a small width parameter. The alpha particles want to cover all the space. So in this ansatz, the only generalization which we did, that we, for the center of mass part, we switched from the small b parameter to the capital B parameter. And then we have a Gaussian, also a center of mass Gaussian, where the alpha particles can cover the whole nuclear volume. So did calculations. Well, before we show any calculations, I want to discuss some properties of this wave function. You see, if the center of mass width is very large, this means particles very far apart from one another. You have a very large width, and the system is very low density. And in this case, when the alpha particles are very far apart, as before, we can neglect the antisymmetrizer. So if if the system at the alpha particles, the small alpha particles are very far apart, it's anyway already a Bose condensate. On the other hand, if it so happened that the minimization of the energy gives you a Width parameter capital B equal to the small b parameter, we have seen that this is just a Slater determinant, harmonic oscillator Slater determinant. So what will be the situation? So we have to see from the minimization what will be the configuration of the Hoyle state with respect to these two values of capital B parameter and small b parameter. Of course, we will assume that for the ground state, the capital B parameter will be close to the small b parameter, because the ground state, as we have seen yesterday, of carbon 12 is more or less well described by a determinant, whereas for the Hoyle state we will probably have a b parameter which is relatively large, and we will make a first calculation of this type. I have to a couple of things. When did I start? At half now? Yes. So this THSR wave function, THSR wave function is then proportional. It's in a way similar to the Kamimura wave function. It has a part which depends only on the two Jacobi coordinates, Xi1 and Xi2, and these three alpha particle wave functions, phi alpha, phi alpha, phi alpha. And this is now not the Kamimura, so this is the THSR wave function, and chi THSR in Jacobi coordinates, it's just minus 4 Xi1 squared over 3 times the width parameter times minus Xi2 squared over b squared. You see now, with respect to the Kamimura wave function, where he varied the chi function completely generally, he did not make any ansatz for the chi wave function. It came out from a minimization procedure. We have now much simplified the problem. We have again expressed the center of mass wave function with only a product of two Gaussians, so where Xi2 this was Xi1 and this was Xi2, Jacobi coordinate, which have Gaussian form with a width parameter capital B. So this is of course extreme simplification. Problem is still complicated. Why? Because you have to antisymmetrize nevertheless, more or less by hand, the whole 12 nucleon wave function. But I mean, this antisymmetrization is not so terrific because there are many there are 4 different fermions, 2 protons, spin up, spin down, 2 neutrons, spin up, spin down, so the different particles, but nevertheless in the 3 alphas you always have protons will spin up, protons will spin up, so you have to antisymmetrize. And the number of terms from the antisymmetrizations goes up very heavily. So it becomes easily 100 terms. And so it's a heavy calculation which has to be done on the computer. So it can be done. Again, expectation value of the Hamiltonian with a given nucleon force. What can I erase here? And so forth. So let us first see, I mean, it is not at all clear a priori what will be the values of these two parameters, capital B and small b. Let us make a first estimate. So we calculate the energy as a function of the capital B parameter, keeping the small b parameter at the free size alpha particle value. And we have we can calculate the ground state as a function of B parameter, capital B parameter, and the excited state. So the ground state we get from E0 is equal, I wrote it already, so it's THSR wave function, H, THSR wave function over the norm. And the excited state, you have to ensure that the excited state is orthogonal to the ground state, which is then a state which depends on the constraining parameter lambda, which is equal to, let's call it again, this THSR state, H, THSR state over the norm minus lambda, Lagrange multiplier, such that the ground state is orthogonal to the first excited state. So in this way you can calculate two energies. One is the ground state, which has a minimum somewhere as a function of B parameter, and you can calculate well, I have a picture there somewhere here actually. So this is the energy curve for the ground state, and this is the energy curve for the first excited state, always 0 plus as a function of the B parameter. And you see already that the B parameter is small at the minimum for the ground state, and it is large. It's a little bit shifted from the minimum here because the eigenvalue of the excited state has some 0 point fluctuations, so it comes here. And you see that with respect to the ground state B value, which is small and close to the small b value, which indicates that for the ground state you have a Slater wave functions. Excited state, several factors, 3, 4 times larger. Now you can already imagine that since the B parameter is large, the whole thing is closer to the condensation picture. You can also calculate the effect of the antisymmetrizer explicitly, which we call here N of B, which is defined as this THSR wave function, the antisymmetrizer. Well, let's call it only the chi part of the wave function of the norm. So this is essentially the effect of the antisymmetrizer on this chi function, and you can see that here as a function of B. Of course, if the B is very large, the antisymmetrizer will not have any effect, and so it will asymptotically go to 1. But if the B parameter got small, Pauli principle is strongly affected, and you see here that for this ground state it's almost 0 here, whereas for the first excited state is above 0.6. So the antisymmetrizer is strongly, the effect of the antisymmetrizer is strongly reduced in the case of the first excited state. So I think maybe we make a break here now, 5 minutes or so, and we continue in the second part to analyze from this point of view of the condensate wave function whether the Hall state actually indeed is some sort of condensation of 3 alpha particles in the same 0 S state or not. So they will go on then in 5 minutes from now. I started at 11:30, no? Yeah.
Can you get also the third state?
Well, I'll come to that. It's a little bit more tricky.
I've been reading the literature.
Yeah, it's a little bit more tricky.
Moshe guy with a very abrasive guy.
Yeah, we know that.
He was a student when he was undergraduate in my courses.
Oh, good. Good, yeah, I know.
Students, he gave me a lot of trouble.
I can imagine, yes.